Hi dear children, this is grade 11 physics topic, energy in simple harmonic motion. The last video we explained about simple harmonic motion and the terms and the definitions and some equations also. I think all of you remember what is oscillation or vibrating. An object that moves to and fro continuously is said to be oscillating, and the time taken for one complete oscillation is called the period. The number of oscillations or vibration per unit time, that is the frequency, and the distance from the equilibrium position is known as the displacement. The amplitude is the maximum displacement. I think all of you remember the values and the words or the terms: period, frequency, amplitude, everything in the simple harmonic motion. And you know that simple harmonic motion is the motion of a particle about a fixed point such that acceleration A is proportional to its displacement x, and we write the equation A is equal to minus omega squared x. Now we are discussing about the energy in simple harmonic motion. Here it is: a spring also has a potential energy when the spring is stretched or compressed. We know that what is meant by potential energy: the energy possessed by an object due to its position. It's called potential energy. But if the spring is stretched or compressed, it has potential energy, which we refer to as elastic potential energy. Because of the elastic potential energy, a stretched or compressed spring can do work on an object that is attached to the spring. Here it is showing the energy conservation in the spring. Okay, the number on the diagram assume that 2 joules of work was done to set the mass into motion. The sum of the kinetic and potential energies must then always sum 2 joule, neglecting the dissipation. Here it is, see, the spring is stretched. Here it is 2 joule kinetic energy, potential energy is 0. When it coming in this position, kinetic energy is 0, potential energy is always the kinetic energy and potential energy is same. But this is showing the conservation of energy. Now comparing simple harmonic motion to a circular motion. The simple harmonic motion and uniform circular motion. The spring and waves behave very similar to object that moves in a circle. So remember that one. These all units are connected. The first unit we started, motion in circle. From that onwards you should thoroughly understand, and the equation is also related to all the units, continuation units also. And see, here it is, the waves are similar to object that moves in a circle. The radius of the circle is symbolic of the displacement x. But here it is, this is a simple harmonic motion. The pendulum is moving like this, and then the displacement is equal to the radius of the circle. And spring of amplitude A, this one is the amplitude, the maximum displacement is amplitude. And here it is, we have to say the x displacement maximum is equal to the amplitude of the wave is equal to the radius of the circle. And here also you have to understand that one. The figure shows the displacement time graph. Here it is the wavelength, and this one is the frequency. And here it is showing the velocity time graph. Velocity is maximum omega lambda, and here it is showing the acceleration of that time graph. This A is equal to omega squared lambda. So the simple harmonic motion is comparing the uniform circular motion. Now what is the kinetic energy and potential energy of simple harmonic motion? Kinetic energy, you know that kinetic energy is an object possessed the energy by its motion. By movement it has kinetic energy. When the spring or the pendulum is moving, it has kinetic energy. But remember that the kinetic energy is given by the equation half mv square. That is the main equation of kinetic energy. Here it is a uniform circular motion. Before we studied that velocity of a uniform circular motion is equal to plus or minus omega root of x0 squared minus x squared. Here we have to, instead of this v squared, we have to substitute this one. So v squared is equal to omega squared x0 squared minus x squared. V squared, instead of in v you have to change this in v squared is equal to So change this root and it will come x0 squared minus x squared. And you have to substitute this v squared in this equation and you will get in kinetic energy of simple harmonic motion is equal to half m omega squared into x0 squared minus x squared. That is the equation for kinetic energy of a simple harmonic motion. Now here the law of conservation of energy requires that the total energy of an oscillating system be the sum of the potential and kinetic energy. You know that what is energy conservation? Energy cannot be created or destroyed. It can be changed from one form to another. And then here it is energy total is equal to kinetic energy plus potential energy. So therefore we have to do that half m omega squared x0 squared, that is the total energy, is equal to half kinetic energy plus potential energy. From here we have to find that half m omega squared x squared. Equation for kinetic energy is equal to half m omega squared into x0 squared minus x squared, and here it is potential energy equal to half m omega squared x squared. From the spring constant you studied that one potential energy, elastic potential energy equal to half k x squared. Here in the simple harmonic motion we have to use this equation. And this graph shows the kinetic and potential energy. See the graphical representation. The total mechanical energy is constant. The total mechanical energy is proportional to the square of the amplitude. And energy is continuously being transferred between potential energy stored in the spring and the kinetic energy of the block. But here it is this green line showing the kinetic energy and this red line showing the potential energy. This is the graphical representation of kinetic energy and potential energy of a simple harmonic motion. We see the total energy is equal to half m omega square x0 square. Potential energy half m omega squared x squared. Kinetic energy half m omega squared x0 squared minus x squared. Now total energy. Remember that the equilibrium at equilibrium point, all the energy of the system is kinetic. There is no potential energy. All the energy is equal to kinetic energy. So total energy of the system E total is therefore total energy is equal to half m omega square x0 squared minus 0 squared will come. So you have to delete this and this is the final equation for total energy is equal to half m omega square x0 squared. Note that the total energy of the system is proportional to the amplitude squared. X0 squared is the amplitude of that one. So this is the equations. Remember all this equation and worksheet we will do some numericals. Okay.